Welcome to part 47.
I
55 or whatever it is. But anyway, we're at 47 minutes into the video now. That's pretty much where we stopped. For those of you that I know want to watch it at home, and I'm going to give you the link here in just a bit. Okay? So, what do we have? What does all this mean? It means the atom is this weird thing. It doesn't follow normal rules. We have to make up a whole new set of rules called quantum mechanics. Okay? So the first thing that we had was Louis de Broglie. He was the French guy by the Eiffel Tower. Okay? He was the French guy that when they were by the Eiffel Tower, the guy was talking about. He wasn't actually that guy. Okay? And he called him Louis de Broglie. And I don't know how you get de Broglie out of that.
What?
But anyway, he introduced the concept of matter waves. That the electron that is traveling in a wave pattern, in a wave property. And he called it that pilot wave. Okay? But he was able to come up with a very simple calculation, whereas h over mv, where h is Planck's constant, if you remember that from E equals h nu, okay? Which we can do the relationship between energy and frequency and wavelength and frequency, and we'll do more problems of that later on this week, okay? But it's the same h as Planck's constant, m is the mass, and v is the velocity. What he found is that any object in motion does indeed have a wave characteristic to it. And so when I take my 100-mile-an-hour serve down the tee, okay, and I'm following that tennis ball, okay, it actually has a wave function to it. But when I put the mass of the tennis ball into the speed of the tennis ball and divide this in, h is equal to 6.63 times 10 to the minus 34th joules. So when we divide that by mass and velocity of anything macroscopic, it's still going to be an extremely small, immeasurable wavelength, undetectable wavelength. Okay? So we don't really worry about that tennis ball having a wave nature. Okay? But when you put the mass of the electron going the speed of the electron, then the wavelength gets to be very measurable. And it turns out that the wavelength is about the same as the diameter of an atom. Okay? Gentlemen. Okay? So, that kind of opened up a whole new thing, and that's what then Schrodinger took that idea. And the reality is, and I'm not sure if there's that E in there or not on the spelling. It might just be C-H-R-O, but it doesn't matter. Schrodinger, okay? Einstein, back with his photoelectric paper, came up with the whole idea of a photon, that light has a dual nature, that it's a wave, but the photon acts like a particle, okay? And so you have a dual nature. So now Schrodinger's saying, well, with this matter waves, maybe we can treat the electron like a wave instead of like a particle, okay? So Schrodinger kind of did the whole idea of the wave function. Now, for us, in our limited math, the wave function has very little meaning, okay? But what it does tell us is when we take the wave function and get each result to this equation and square it, it gives us a probability of where we're going to find the electron. Now this is where Heisenberg and the Schrodinger are all kind of mixed together, because Heisenberg uncertainty principle says what?
If you know the speed of the electron, you do not know the location. If you know the location, you do not know the speed.
Okay, location and speed. The more you know the location, the less you know the speed. The more you know the speed, the less you know the location. Again, my 100-mile-an-hour tennis ball going down there, when you plug it into the uncertainty equation, the uncertainty of where it is or how fast it's going is incredibly, incredibly tiny, insignificant. So the reality is we can know on a macroscopic scale, you know, which we envision, exactly the speed, and we can know exactly the location at any given moment. But when you get, again, down on the size of an electron, uncertainty gets to be very, very, very large. So we can't know exactly where the electron is. So instead of saying the electron's in an orbit around the nucleus, what do we say it's in? an electron cloud, but within the electron cloud we have specific SPDF, we call those orbitals. Okay? And the orbital is defined as the most probable place to find an electron. It's where it might be. So we have the SPDF, we already kind of talked about that. So how do they come up with those shapes? Well, when you plug in to the Schrodinger's equations, and we remember quantum numbers, n, l, m sub l, m sub s, we plug those values in. If we put in n equals 2 and l equals 1, and then m sub l, I don't know if you pick one, a -1, a 0, or a 1, you put that into Schrodinger's equations. You guys are used to just getting one, maybe two answers to when you solve an equation. What's the value of x? Well, in Schrodinger's very complex, you have a multitude of possible answers. When you take the answer to that wave function and square it, it gives a probability of where it's going to be in space. This is an electron density map when you put into Schrodinger's equation and you get the wave function squared. This is, each dot represents not a different electron, but a different place one electron might be. Okay? So notice it's darkest right here. This is the greatest probability of finding the electron in that area. So we do our shape and we say an orbital is defined as a place you have 90% probability of where the electron might be. How it's traveling in this space, we have no clue. We just consider it to be in some kind of standing wave pattern. Okay, and I'll get to that in 1 second. Okay, so we call this an electron density. So we shape that. We need a little bit more structure. So we kind of draw these models like this. But the electron in no way is confined to this space. This is just a 90% probability of where it's going to be. So we no longer can say anything exact about the electron and its position because the Heisenberg uncertainty principle says it's impossible. Okay? So, if we go and do the same thing on your d orbitals, you get electron density map that looks like this. Okay? So we see this one here, it's going to be kind of like this one, and there's just different orientations in space, x, y, z axis, that these can be on. This one's kind of my favorite one. It's like a p orbital with a donut around it. Okay, and so here's the p orbital and here's the donut around it. But again, it's all based upon the energy that the electron has. So it's now thought that the electron is traveling around the nucleus in a standing wave pattern. Okay, Zane, here's the closest one you need to grab the end of this and walk to the end of that wall. Pick an end. See if you can undo that. If not, there we go. Good job. All right. All the way to the wall. Okay? So if I take this, just spring, and I send a pulse, you can see the pulse going back and forth. It reflects off of Zane, comes back to me, back and forth, back and forth. Okay?
I'm trying.
Now,
I'm trying.
okay? But if I do a continuous wave, I can now make what's called a standing wave pattern. Okay? And so we have, notice we have the two envelopes, and that's where constructive interference is taking place, where crest is meeting crest, where trough is meeting trough. And so it's going double high or double low. And right in the middle is destructive interference, where a crest is meeting a trough and they're canceling each other out. We call that a nodal region. Okay? Notice that there's only two envelopes. There's got to be a certain, go ahead, you can stop. There's got to be a specific energy for me to be able to form that standing wave. Now, if I want to change the energy, okay, if I don't get it just right, we have chaos. Ooh, 4. Okay?
Oh.
Now I've changed it to where I have different numbers of nodes and envelopes. Okay? But notice again, there's a whole number of wavelengths, a whole number of envelopes. There's only certain wavelengths, there's only certain energies that's going to be able to form that standing wave pattern. Schrodinger used that. Go, thanks, Lisanne. Schrodinger used that idea to be able to explain Bohr's energy levels in terms of waves. That there's only certain distances from the nucleus that the electron can be in order to form the standing wave, and there's only certain energies it can have to be in those wave patterns. Okay? So, as a result then, with the Heisenberg uncertainty principle, Schrodinger's equations, and everything all put together, we now have our model which, again, we're trying to get something, but we know that we have 1s, 2s, 2p, 3s, 3p. We'll talk about why there's an overlap, 4s, 3b, 4p, 5s. Oh, I forgot my 4f. 5s, 4d, whoop, 4d, 5p, 6s, then my 4f, 5d, 6p, whoops, 7s, 5f, and then 6d, 7p. Now that's as high as we go, because at 7p, we're to the end of the road here, but even anything above uranium, it's all man-made, they only last for fractions of a second, so they don't have electron clouds anyway, so really, up to uranium-92 is as much as we need to go. Alright, we'll continue that and review how to fill this in on Thursday.